says all of these internet forums I've read, so it's not reliable.
All right, this is where we left off. So make sure you open up your R and have that ready. And hopefully you did this and worked through it. And we will step through an analysis. So give me a few minutes as you get this stuff opened up.
I can't imagine it would be, but I mean, I guess I'm gonna find
Have you
out.
considered building your barbecue?
That's right.
That's a good idea.
No, I haven't. Is that kind of like the BJ or?
That's a really good
Like what?
idea.
Is that kind of like the BJ or?
I think so, yeah. Yeah, it's acidity.
Barbecue.
It's a chemical process.
Cotton candy brisket. Zombie brisket.
Oh my god.
Very good, like, lovely, like.
A banana pudding? No.
Brisket does?
Yeah.
Yeah, you get it spinning real fast, it stretches out and it's very thin. Fire.
So
you blow Cheerios on it.
it'll take breath away.
You guys are gross. I don't know. I don't know what I'm gonna do next. I gotta get rid of all these corn chips though. Why you like it? Okay, it's more mild flavor. Or a more robust flavor. Well, that's stout. Yeah, I was in the ski for the injury. Yeah, post coat would be good. That's how traditional Texas barbecue is good. Post coat. But we got so much to eat that I didn't eat all day now. And it tastes great. I'm gonna do it with juniper though. I think it's good. Juniper. I don't know if that's like or cedar stage.
Yeah, like that's what we don't do, Atari, like.
Yeah.
Most
people
people
don't
don't
smoke
smoke hot dogs. Okay.
What are you cooking over 2x4?
I don't know, it's in East Texas, so I got pine and those around.
It is.
Behind the
There's
counter.
a little bit of.
Yeah.
Hope this lasts about this long. Right over there?
More than all right, we're getting.
Sure, you're a panic. Sapphire and Shark Class. Honestly, what it really looks like having just on an awesome adventure with Bill and Ted.
What is
You
it, something?
know what it is? You know what that is?
No, yeah. Y'all know how weird Al is?
That's your
Yes.
Am I like,
How dare you be so formal
Am I, like-
with him?
bad for not knowing who that was?
Well, you said what Bill and Ted's awesome adventure was, so it's kind of worse.
What?
Especially wearing a shirt like that.
Ah, make fun of my shirt one more time.
Right. You sure just having like a
All right, we'll see if Rebecca is watching. But she had an error. She kept getting an error with her permutation test, poured out perm dot test, and had written her back. I think you need to check it, Rebecca, but these need to be on different lines. So I think yours looked something like that. And I think you would have had an unexpected error because there's no space that kind of separates it. If you need it on the same line, you can always use a semicolon. But try that, and if that doesn't work, then just go back and change all of these to, delete them and make them yourself, remake them, because in case of the copy and paste, it didn't quite work. But try that out. All right, so our goal here, flower visits. Figure out which of these variables will affect the number of pollination visits. Right? So how did it work out? All right. So I know there's some stuff on the presentation. We're going to skip a lot of that, and we're going to go through, and I'm going to explain how I went through it, this type of analysis. All right, because once we start working with continuous variables, you can start to see some funny things happening, including when you use GL multi, it takes absolutely forever to find a model. It keeps finding the same model, but it never ends until, I don't know, 50,000 iterations or something like that. It takes forever. A lot of times that could be due to correlation between the variables. So R has a hard time trying to figure out which one's best. So how do we handle that? Well, we handle that by first checking that variance inflation factors first and removing anything that looks like it might be dangerous or might be highly correlated. If we do that, then hopefully we avoid the initial problem that we have of GL multi taking super long, and even when it reports a model, we've got 3, 4 different interactions, including 3-way interactions, 4-way interactions, and so forth. All right, so this is my flower visits. I called it FV for flower visits. So let me import my data set here. Yep, flower visits. I called it FV just to make it a little bit simpler. And I'm going to load my libraries. So the ones that I used was CAR, GBLMA, GL multi, and if we need anything else, we'll add it at that time. All right, so the first up is to check our assumptions, right? So I just make full model, all interactions, and if I run GVLMA, I'm going to get this error message. It says, system is computationally singular. All right, it can't basically give us an answer. So we have to default then to checking our residuals. So I make plots of the residuals, and I already have an idea that I'm going to use AIC to simplify. So you may wonder, why are we doing this? Well, we're doing this because once we find the simplest model, if we meet our assumptions, then we can go back to using classical tests to confirm that we did find the simplest model, to confirm that all variables in our model are significant, to run our 2 keys or any post hoc tests. And that's really why we're checking it before we run our AIC. So everything's really looking pretty good. Nothing looks out of the ordinary. So then we have our simplification. And I've broken this up into 2 different methods. All right. So in our first method, we're going to start with the full model. All right. I'm just going to take that full model that we used, and I'm going to run it. All right. And some things that I did here was I have report equals F and plotty equals F. So as you know, when you run this GL multi, it produces all those IC plots. All right, so plotty equals F says, don't give me those. We don't look at those anyways. All right, report equals F says, basically, suppress the output. Don't tell me how many models you're making. Now, this could be dangerous because if you have report equals F, it just keeps running and running and running and running. And you're like, well, did I do something wrong? All right, so for this, I did report equals F, not because I didn't want to see the output, but because I converted this to a PDF. All right, and I don't need those pages of models. What's important is looking at this output. All right, so I look at the output, I can see corolla diameter, color, petal width, and stamen look to be significant terms. We have petal width, corolla diameter, petal length. All of the rest are pretty close, but not up to that 80%. So I'm going to go ahead and take a look at the weight table to see what it's telling me. And the very top one is saying, hey, we need to have at least 3 of these interaction terms in our model. All right? And that's not something that I want to deal with. All right? I can see that number 2 is actually a lot more manageable. All right, so what about the AICs? Well, we start at 254.8. All right, our rule is 2. So you can see that we don't really break that 2 until we get down here, down to our 10th model. And this is also kind of a trick. I did weight table output 1 to 10. All right, just because I want to look at the top 10 models. If you have like 20 models all within 2 AICs, probably need to go back and look at some stuff. So what's going on here? Why do we have a bunch of these interactions, and then on the very next model, 2 of them dropped out? 2 of them dropped out. These 2 dropped out. What's going on? And not only that, but check this out. Petal length appeared in this top model, but petal width appeared in the second model. We've got some funny things going on. Normally, if we go back and look at some of our data, some of our tables, our weight tables, it's a pretty good progression where our simplest model is up at top, and then we add another term, or we add 2 terms, and it kind of builds on top of each other. But in this case, we have this really complex model listed at the top, and then a much simpler model listed number 2. So why is that? Hold on. Also, if you look at the interactions that are included, this is stamen and petal width, right? Where is stamen and petal width as our main effects? They're not there, right? Look at corolla diameter and petal width. All right, we already said petal width is not there. Corolla diameter is, but petal width is not. Here's one that has petal length and corolla D. We violated one of those requirements that says if we have an interaction term, then we need the main effects of those terms. So if we factor in these 2 interaction terms, we also need stamen to appear in there, and we need petal width to appear in there. But that model doesn't happen. So how do we fix this? There's this output option called marginality. Marginality forces GL multi to make sure that if it includes an interaction term, it also includes its main effects. All right? So that's what we're going to do. I'm going to rerun this using our full model. All right? This time I've got the report. I didn't say report equals F so that we can see it. But I'm going to force marginality, or force that condition where if we have an interaction in our model, the main effects in that interaction are also included. See it? There it is. Not terrible. It went down to 1,500 models, basically. And then it produces this output. So notice now, our model looks a bit different. We've got stamen, corolla diameter, petal width. We've got color. We've got these other interactions down here. They're all below the 80, but they're still relatively high. All right, what does our weight table look like now? If I look at the weight table, now we still have our top model with an interaction. All right, we have a top model with our interaction. The interaction includes both of the main effects, so petal width and stamen. There's our main effects for that interaction. And then we also have corolla diameter and we have color. All right, not bad. Second model is basically a model without that interaction. All right, hey, that's not too bad either. When we look at the AICs, you can see now that our 2 gets us right down here. So basically we've got 6 models to consider that are all within 2 AICs. Now, at this point, since we know our assumptions are met, we can go back to doing classical tests. We can use GL multi to kind of get us close to the simplest model, and then we look at Anova tables just to ensure that each of our terms is significant. So I'm going to create the simplest model, and what I did was created that top one, this one. All right, so I've got color. Oh, I did not. I had petal width. Did I drop something? Did I leave something off here? Petal length, petal width. What are? Come on, let me move this. I need to see my. We got color, petal length, petal width, corolla diameter, standard. All right, we're good. Have to is that? Scroll down here. All right, so we've got pedal width. Actually, no, I started with down here. And it doesn't matter. I would probably start at something, I know I started here because we're in the top 6. I know I started here and started looking at Anova tables from that point. But I'm going to abbreviate it. And we started at pedal length and width. We started at this one. Corolla diameter, stamen, and then stamen plus pedal width. So I started here, still within our 2 AICs, and I looked at our Anova table. You can use the type 2 because what I'm interested in is this interaction term first. That's the highest order interaction term. So with the highest order interaction term, I can see from my Anova table that that term is not significant. So one thing that we can do now is just go ahead and drop it all and recreate our Anova table. And at this point, it doesn't really matter if we're doing a type 2 or a type 3 because we have no more interaction term. We've reduced it. But what we also see now is that pedal length is no longer significant based on our Anova table. So we can go ahead and remove that, look at our Anova, and now we have these 4 terms: color, pedal width, corolla diameter, and stamen. How does that compare with our GL multi? Well, that was number 2 on our list. All right, that was number 2 on the list. And you would get to this if we started at number 1. If we did an Anova table of this, you would see that stamen and pedal width are not significant. You drop it, and it gets us down to here. So since all of our assumptions are met, I'm going to go ahead and conclude that we have our simplest model, which is color, pedal width, corolla diameter, and stamen. Now, at this point, we have our simplest model. We can go ahead and check our variance inflation factors. All right, and I kind of cheated. I did VIF first, so I had the GVIFs, and then I went back and squared it just to look at it, and everything looks good. No problem. No problem. So at this point, we have our simplest model. And I go ahead and create it. And now we have post-hoc tests to deal with. All right? We've got to look at the relationship between color and visits. We have to look at the relationship of pedal width, corolla diameter, and stamen lengths with visits. All right? So that's our next logical step. And we'll do that. We'll look at that. Questions? All right, there are some times where it's going to take a lot longer to run the GL multi. Right, you've just got a massive data set, or you've got a lot of different variables. Right? This is where our second method of model simplification comes into play. All right? And this is going to apply when you have continuous variables as independent variables. So instead of creating our full model, we've already done that. All right, we've already made our full model. We've already checked the GVLMA or the plot of the residuals. Things are looking good. But now what I'm going to do is take that model and create a main effects only model. All right, this model is going to be used to check for variance inflation factors. We're going to check for correlations. All right, so I'm going to create this main model first. We haven't even simplified it, because that's not the point. And then I'm going to look at our variance inflation factors. And again, I cheated. I actually did this first, saw I had the GVIF table, and then I went back and just said, okay, well, we're looking at the square of those values. And I can see right here that I've got some problems. And it looks like these 2 variables, pedal length and corolla diameter, seem to be correlated with each other, right? They've got high values. Right, it's above 5 is what we're looking at. All right, so this suggests we violated that multi-collinearity assumption. And this might be why it's taking so long to find a simplest model, because it includes 1, and it goes down to one set of simplest models. If it includes the other, you get a completely different set of simplest models. So you've got all of this randomization that's happening, different starting points, trying to find that simplest model, and these things, the correlation is causing us problems. So with this second method, what we can go ahead and do is update that main model, remove petal length. I'm going to remove petal length because it has the highest generalized inflation factor. All right, I'm going to remove it, and then I'm going to go look at our new table, and you can see everything gets fixed. Everything gets fixed. Why did I remove petal length instead of corolla? One, it was the highest, so I started there. But then number two, we can think about what we're actually doing. We've got this flower, right? You've got petal lengths, you have petal widths, and then you have the corolla diameter. What's a corolla diameter? What's that?
The whole flower.
Yeah, it's the whole flower. It's the whole flower. All right. So it kind of makes sense if you think about it biologically, is that the length of the petal, the larger the petal, then the larger the corolla diameter. But from a biological perspective, if we're looking at pollinators, do you think they're responding necessarily to the length, or do you think they're responding to the total diameter itself? Probably the total diameter. Or at least that's kind of the assumption. So, I think that's a valid reason for why you would drop petal width or petal length to say, okay, we're going to focus on corolla diameter. When we do that, now we're good. All right. So once we have this, we have these four variables. We've satisfied that independence part of it, or the non-correlation part of it. So now I'm going to make a different full model that is only color, petal width, corolla diameter, and stamens. So we've dropped out that one of those variables that was correlated with another one. And then from there, so I just called this model full 2, and then I'm going to run the output, or the GL multi, and notice how much quicker it finds our model. Right, before it went up to 1,500. This time, hit 100 models, found everything. Found what it needed to. Do you think we found the same one? Looking at the plot, yeah, we got stamen, corolla diameter, petal width. We got color. All right, we got those four. We've got these other interactions that pop up, but they're not at 80%. What about the weight table? Same thing. We're seeing something similar occur. Our top one includes an interaction. The second one does not. If we look at the AICs, they're close to each other. And now you can see our within 2 AIC units, it's dropped down to 4 models. So from here, I would go back, look at our models and say, okay, well, let's check to see which of these is going to give us a model that has significant terms. And again, why can we do that? It's because we met our assumptions. We met our assumptions. So the first one that I did was took the corolla. Took this one. Took the most complex model in that group of 4. Is what I did. And created that model, and I looked at the Anova table, and I can see right now, and again, it can be type 2 because we're just looking at our interaction term. Type 3 gives us the same p-values. These are the ones that we're looking at. So I've got both of these are suggesting that they are not significant. So I'm going to remove that petal width. And I remove petal width down here. And this petal width and stamen is still significant, or it's not significant. So I update that, check our Anova tables, and we're back to the same type of conclusion. I'll change that to Anova type 2. Color, petal width, corolla diameter, and stamen. That's how I did it. I have this second model here as a demonstration. So you can say, well, hold on, I took the most complex. Why isn't this one considered more complex? Well, you're going to get the same thing. So I did both of these. That's why I have mod 4 and mod 5. Just to demonstrate that we still have the interactions that are not significant. So no matter where you started with, which of those complex models you started with, we're going to be dropping those interactions. And they would ultimately get us to here, this model. All right, so method 1, we started with the full model, took 1,500 iterations to find the simplest model. And then, you run the VIF, it looked okay, but that was because corolla diameter and the petal lengths dropped out. So let me run these together. In the end, both methods arrived at the same simplest model. All right, so which one do I prefer? I prefer method 2. I prefer looking at our main effects first, checking that VIFs, the variance inflation factors first, correcting those problems, and then simplifying the model. Now, just from experience, it seems like that has relieved a lot of headaches. Because there's been times where you run the GL multi, it takes 50,000, 100,000 iterations. You're sitting there just waiting and waiting and waiting. And then it comes back and it says the simplest model has like all possible interaction terms in it. It's like, what the heck? I waited 30 minutes to find that out. All right, and then you go back and you check your variance inflation factors and you find out that half the variables are highly correlated. It's like, well, I just wasted all of that time. So I prefer method 2. Remove those terms that are correlated and then simplify. And when you get to your weight table, since our assumptions are met, go ahead and start checking the Anova tables and continue dropping terms until you find the model that has all significant terms. You'll see that it is that one. It's typically going to be one of these that appears as one of our top candidate models. Questions on that? To the what?
To the 2D.
I didn't get to there yet.
Oh, okay, I didn't know. Here we go.
Would you just recognize this? You're like, I'm working with these variables and I have all these interactions. I check these.
Yep. Yeah. So you input, you're working with the data, right? It's your data. So if you sent me, your data and said, hey, can you help me? I'm trying to simplify model. One of the first things that I'm going to do when I get it into R is to go ahead and look at the summary. And right here, I'm saying, holy cow, I've got a lot of continuous variables. And with all these continuous variables, I need to check to see if they're correlated. And again, it'll save you headaches if you remember to check that first.
Yeah, when I did this, we got to the GL multi, and I was like, I guess I was more lazy. I was like, screw that, I don't want to do all those interactions. So I just went to the weight tables, not the weight table, the Anova table.
Yep.
From the start, which is a nightmare too, because it was like 28 mods.
Yeah, so there's nothing that says that once you decide to use AIC for your model selection that you always have to use it. If our assumptions are met, you can use the AIC selection to get down to a set of candidate models, and then finish it out using Anova tables. Because our simplest model is always going to be the one that explains the most variation with the least amount of variables. In other words, every single variable is a significant predictor of that dependent variable. All of those variables in our simplest model should be significant. Yep, it is. Treat. All right, so any other questions? Go down to
a summary of my simplest model. I have the same simplest model that you did, but when I did a summary of it, it included red and white, but not pink.
Yep.
Why
is that?
Great question. If I knew, I wouldn't have questioned.
All right, while you ask that, all right, so, all right, we know these are the variables, all right? These are the variables that are significant. And then that next step is to explain that relationship, all right? We need to explain how does petal width affect pollination visits? How does corolla diameter affect pollinator visits? How does stamen length affect visits? How does color affect visits? All right, so we need to take it that next step to explain that relationship. So color was first. All right, so with color, we can run Tukey's. Works out, we don't have an interaction, so we don't have any subsets we have to worry about. But we've got, I have multi-comp on here. We're going to compare them. So we're going to use Tukey, HSD for that one. So something we have to remember is that we have these covariates. They're continuous predictor variables. All right. So we ran a Tukey's. It looks right now that all the colors are different. But that just looks at the means. What we want to do is adjust for the diameters and the sizes and the lengths, and then compare color. So to do that, we're going to use the GLHT function that's in multcomp. We are running it on simp. It doesn't matter, method 1 or method 2, where our linear function is a multiple comparisons procedure, and we are running it on color. It's on that variable. Color, we want to run Tukey. Cannot find GLHT. Scroll up. There we go. All right, I got my multcomp package loaded. That should now work. All right. So we arrive at the same answer, that all the colors differ. Pollination visit depend on the color of that flower. Question is, which one is better? Which one is preferred? Or perhaps I should say, which one is correct? What do you think? What do you think? Think they're the same?
I do.
Okay. Okay. We got slight difference. Okay. Do you remember why we used the GLHT? And we introduced it real early on when we introduced Tukey. We said, hey, we get the same answer if we use Tukey HSD. But then we came back to it. We said, we're going to have to use this some of the time. What's that?
Type 1 error?
Well, we're doing the Tukeys to control for inflated type 1 errors. But what's the difference between the Tukey HSD and the Tukey in the GLHT package? I can't visits as a function of color. Alright, get our same. Here's our means. So pink flowers had 108 visits, red flowers had 138 visits, white flowers had 78 visits. Alright, they look different. We'll see. We'll do this. I'm going to copy this because we're going to look at all of these. All right. Here's color, or petal width. It's a function of color. It doesn't look like our flowers, or at least the petal widths vary by color at all. It doesn't look like it. That's pretty good. What about corolla diameter? Still, they look pretty close, right? They look pretty close. At least the medians are looking like they line up. Here's stamen. Any different? Probably not. Probably not. But if we cycle through these, it looks like, pay attention to the red right here. We're lined up pretty darn close. It's a little bit higher. A little bit higher. It almost looks like the red flowers might be slightly larger than the pink and the white. And that could be important. This Tukey HSD function, Tukey HSD on the AOV, is comparing the means, mean visits of the three different colors. It ignores any relationship color has with all of the other continuous variables in our model. So it's just looking at these raw numbers. The GLHT function looks at this model, at the simplest model, says, okay, we've got petal width, corolla diameter, and stamen length, right? After we account for those measurements, after we try to get everything controlled, if we control for all these different lengths and sizes, what's the relationship between color and visits? So to remember how we calculate our covariate adjusted means, facts package. I'm going to go back and add that to my libraries. Facts is loaded. Go down here. Bottom yet. The term that we are looking for is color. The model. We're interested in comparing for this. Anytime we're going to have a continuous variable in our model as an independent predictor, we want to account for all of the continuous variables before looking at the effective color. You can see that there's really not a huge change. Let's just run that and get them closer together. 108.13321, 108.075. It's pretty close. 138.3, 138.1. Again, pretty close. 78.1, 78.3. Pretty close. They're pretty close because our flower colors, the flower sizes were similar across the colors. But if you had a drastically different size, let's say white was the smallest, pink were middle, and red were the largest, hey, you probably need to figure out, after we control for size, is color still significant? Tukey HSD does not account for that. That's why we use this. But as you can see, they're so different, and they're really no effective size by color. Or color doesn't affect size, or is not associated with size, that we don't have to worry too much about. All right. What graphs would you present? Visits as a function of color. That works. Or reporting these mean visits. And probably I would report, these would be the correct ones to report. But I don't think anyone would necessarily give you any trouble if you report these and just say that sizes didn't differ by, all your different variables, your sizes didn't differ by color. So that's our color. What about the continuous variables? There's really no post hoc test for the continuous variables. All right, instead what we're looking at is trying to describe the relationship. All right, the relationship between visits and petal width and corolla diameter and stain. So for that, you can look at the summary table. All right. So for petal width, we look at this. So we can see that as petal widths increase, the number of visits increase. Corolla diameter, as the flowers get bigger, number of visits get bigger. Stamen, as the stamens get bigger, the number of visits actually decrease. All right, that's our relationship. Can we add numbers to it? Yep. Yeah, for every 1 unit increase in petal width, we add 0.8 visits. For every 1 unit increase in diameter, we add 1.2 visits. For every increased unit in stamen length, we lose half a visit. All right? That's our interpretation. No post hoc test. It's just look at the summary, verbalize what that relationship is. Now we had a question, color, and you can see it in this formula, or in this output. It has color red, color white. Like, where's the color pink? Well, it comes down to, what do these estimates mean? These estimates mean slopes of the lines. So we start with the intercept. The intercept is our starting point. So this is for petal width of 0. It's for a corolla diameter of 0. It's for a stamen length of 0. All right. It's for what color plant? It's the pink. It's the pink. So then, if we change it to red, we're adding 30 more visits. If we go from pink to white, we lose 30 visits, and that kind of is replicated here in the number of visits. 30, difference of 30 between pink and red, and it's about 30, right? We get a drop of about 30 from red to white, or not from red to white, from pink to white. It's also a drop of about 30.
So what do the numbers actually represent underneath each color? They're not number of visits, or are they average?
It is. What, these? Yeah, they represent.
Underneath color, after
this?
the aggregate, or underneath, the effect function.
Yes, the effect function.
What is that 108, 138, 78?
That is the average number of visits for that color after we account for the sizes in our model.
Okay.
It's called the covariate adjusted means. So yeah, I mean, some of these flowers, it's not going to be exactly 108. You could have 115, 120. You could have 90. But the average is 108. And that's the same thing with our slope here. The average, 29 or whatever. And then how do we, what kind of graphs can we do? Did do a graph on here. I think it's probably one of the, here it is, one of the more useful ones. one of the more useful ones. And we went like, a scatter plot is going to be sufficient. So it's just main effects. If you did scatter plots of petal width as a function of visits, that works. If you scatter plots of corona depth as a function of visit, that works. If you do it by color and say this is for the red flowers, this is for the pink flowers, this is for the white flowers, that works. Or you can condense them all onto one graph where I use black, red, and blue to indicate the different colors. Could have used red, pink, and white, but the whites would have been hard to show up. All right, so this is basically, I did my subsets. Or I plotted, I did color as numeric color, because again, that's part of our palette. So I specified what colors I want to use. And then I added a best fit line. So the best fit line is AB line. And it'll take, actually, the linear model. So you basically say, what's the equation of the line that we want to plot? Well, for the red one, we want to do petal width, or visits as a function of petal width, where we're only looking at red flowers. And that works. And this is for petal width. Corolla diameter works the same way. You would just replace petal.w with corolla.d to produce these. And again, if you're looking, if you want to do these, or if you're interested in making these, I'll help you out. It's no problem. Again, kind of making graphics, we could take an entire semester to do these things. And that's basically the write-up. So, a couple of really key things. When you work with continuous variables, the variance inflation factor is, you're going to have to check it when we have 2 or more continuous variables. All right? When you have 2 or more, that's when you should check it. And the procedures, my recommended procedure is to do that method too. First do the full model, check your assumptions, and then make a main effects only model and check the VIF. And if you have problems of correlation, fix those first. And then try your GeoMulti.
When we're doing the write-up on the VIF, do we just include the last column, like the GVIF squared thing, or do we just, I guess we probably include the degrees of freedom too, but is it like everything?
Oh, in the write-up.
Yeah.
For the VIF. Get to it. Yeah, the 2 second method, here it is. Something like this. You probably only need to report the one that's problematic, and you would do the square of the VIF, so that you would report that. Just 2 decimal places will work. You might have a reviewer that would ask for a scatter plot between petal length and corolla diameter, and maybe even asking you to calculate a correlation between those, just to kind of demonstrate that there is a high correlation. But the correlation homework should be fairly easy, right? Hoc Test. But yeah, that's what you could report. So check your VIFs, fix any problems, and then do your model simplification. Again, starting with the full model with any of those correlated terms removed. Once you get down to your candidate models, if all of your assumptions are met, go ahead and proceed with making Anova tables to confirm. All right. Once you find your simplest model and all terms are significant, then we move on to our post-hoc tests. Post-hoc tests, if we have a categorical variable in it, and it's more than 2 levels. So if we have, let's say, sex, male and female, you don't need 2 keys on that. You just look at these, the covariate adjusted means. That tells you which one's larger, which one's smaller. The graph will probably show you that too. Which one's larger, which one's smaller, that's it. But if you have 3 or more levels, then you're going to need to use this. Right? You're going to need to use that. If you have, for your continuous variables, there's no post hoc test. Rather, you just look at the summary table, and then you report these estimates, or you describe the relationship. All right. Now, what happens if we didn't meet our assumptions? All right. If our assumptions are violated, we still have these four. I'm going to say we violated the assumptions. We've got these four candidate models. Trying to do randomization tests on these models would actually be somewhat difficult. This top one, not so much. But it's one of those restricted permutational Anovas where you're going to have to, we're checking petal and stem, we're checking these two. You're going to have to fix color and corolla diameter. That's going to be our strata, the combination of those two, and then you're going to have to shuffle, which basically breaks up the stamen and petal width association, and that you're just checking to see that's significant. If we have to go down that route, I will help you on that. For this class, we look at these four candidate models, and what is always our conclusion? Or what is our conclusion in picking a simplest model, or most parsimonious model? Yes, that is the conclusion. You always pick the simplest one, yeah. Right? Which of these is the simplest one? Yeah. You violate the assumptions, go with the simplest model, go with this one. And again, I didn't say, well, I'm taking the simplest out of these top 10. Those are all within 2 units, 2 AIC units. That's our candidate model set. Those are the ones that we're looking at. And pick your simplest one here. And there are some. We've had some that have been really complex interactions. And there's really no way to get around it. All right, questions? Let's add some additional info here. The reason I use those reports, report equals F, was so I can make a PDF and I can get this posted. So you actually have this flower visits kind of working out. So we're trying to color which colors differ. 2Ps, HSD. Works well when all predictors are qualitative. We don't have that here. So there. When all of our predictors, when all of our X's are qualitative, when they're factors, categorical variables, 2P HSD works well. Right. GLHT is preferred. Treatment is preferred. It's required if we have continuous or numeric, I should say quantitative. Function in GLHT compares covariate adjusted means. And calculated using the estimates package. So kind of clarify that. And then determine the relationship between visits and continuous variables is as easy as looking at the summary table. Estimate. So the estimate explains the relationship. So it's either a positive or negative relationship. And in this place, it would be more of a correlation since we didn't like manipulate manipulate values. Right? If we like went in and actually cut flowers to certain sizes, then we can show cause effect. All right. But if we just measured stuff, it's more of a correlation. So this would be positive or negative relationship, and also magnitude. So the larger the estimate is, the more of an effect we'll see. All right. Not bad. All right. Any questions on that correlation homework?
Are you gonna post the PDF?
Yep. I'm gonna post that because we're about done here. Yeah, so I'll post that. I'm gonna post the flower visits up, make a PDF so you have it. Note again, I did use report equals F to suppress this output of, where is it? Yeah, the GL multi. That's one option, and also the plotty equals F kind of suppresses that plot output. That can work as well if you did results equals F. However, sometimes results equal F won't suppress it completely if you don't have this plot function on there. That's what I've figured out. So if I didn't have plot on here, it'll give the full output. But if I do results equals F and then have the plot, it suppresses all of the output from this GL multi and will only report the plot. So I think it's just a little bit easier to pass the plot equals F and the report equals F right to the GL multi, that I don't have to sit and watch it. All right, so I'll get this up. All right. Now, final exam. Oh, the exam key was posted. Should be accessible. Exam 1 key was posted. I didn't realize that wasn't up. I did explain some of the same stuff, and again, kind of point out that we can use GL multi. We can use AIC to simplify our models, and it can get us close. So one of those things, if our assumptions are met, go ahead and take that next step. Make some of the Anova tables with some of those candidate models, and see if you can get a model where all terms are significant. Try to do that. Final exam. Believe it or not, I have the take-home part done. Oh, that was a pain. And I will warn you that there might be 1 or 2 GL multis that take a long time to find. It's because it large sample size. So it won't take like 30 minutes long, but it could take a minute, 2 minutes. Sit there thinking, man, it's not time. So let it work. That'll go live 9 a.m. on Friday. Take home part. And I know I said we were going to have it due on Wednesday at 6. I'm not going to look at those things until Thursday morning. So I'm just going to make the due date 9 a.m. on Thursday. So I'll be here in my office. So if you have problems getting things knitted, I can help you out. Just stop by, bring your laptop, or we can meet. You can come down here, and we can get it fixed. But yeah, the plan is I'm not going to look at those things until Thursday. So no point requiring it to. Which means then on Wednesday we don't even have to meet that evening. You'll be around. I definitely suggest not waiting. It's 100 points. So it goes back to some of our simplest, that exam 1 where it's testing single variables, doing like a one-way Anova, two-way Anova, and then our correlations and our model simplification. All right.
When is the Blackboard part going to be due?
The exam part?
Yeah.
The exam part, my plan is to have that posted on Monday morning, and then it'll be due Wednesday night.
Okay.
On that one, I go in and I look at the questions and see if there's any questions where no one gets it right. And then oftentimes that's the problem with the key. The answer was marked incorrectly. Other ones I look to see if, if it's out of 1 point, if there's one, the class average is 0.25, I look to see what was the answer. Was it a good good question? But yeah, we'll just do Monday through Wednesday.
How many points is the theoretical one?
I don't know. I haven't made that.
Okay.
I haven't made that one. But the theoretical one will also have some, some definitions. It'll be a lot of the same, where I might describe the problem and ask, what's the appropriate test? What are the assumptions of a t-test? What's what type of variable is it? What's the scale? But in this class, it's been a lot more about the application. It's about how to actually simplify models. What do you do when you run into problems? All right, and once it gets that one would go live sometime Monday morning, and then I'll probably post an announcement and just say how many questions, how long it should take. I can tell you, I'm not planning like a 50, 60 question test.
That's nice. 20 questions for that point of view, right?
I don't know if you want that. So, all right.
We're ready.
All right. I think we're good. I would definitely look over the keys. Kind of go through. My keys did make use. I do have it on the exam part. Make use of that cache function. So. Here, let's say this output. And say as you're running it, you find out that this thing takes absolutely forever to run. Add cache equals T for it. All right. When you first knit it, it'll save the cache. And let's say, here's the other thing that I think I found out. You got this running, but let's say that this one screws up because you added an extra comma or something like that, right? The knit's going to fail. That doesn't mean that it has to go back and recalculate this entire thing, all right? It cached it already. The next time you run it, it should zip through this no problem. Can't guarantee that that's what's going to happen, but I do know that once you successfully produce a knitted document, and the next time you run it, it doesn't take nearly as long. It'll zip right through because it saves all of the output on your computer. All right.
So should we do that with our permutational test?
Yeah.
Time-consuming stuff?
Yeah.
Cool.
Well, it's been fun.
Yeah, thank you. I have to get this transferred. But yeah, I'm going to get the stuff posted right before I leave.
Oh, they could take it if you want.
Yeah. Go ahead. I would be gone. I'll take a look at it. Yeah. Yeah, I see it as a